Hi everyone, today we're going to be presenting on tiny mosquito detection models for deployment on a low-cost MCU. Starting off with our motivation, mosquitoes cause millions of deaths per year due to their ability to cause diseases like malaria and Zika. And because of this, the CDC actually characterizes them as the world's deadliest animal. However, current methods for mosquito detection and monitoring in affected areas are rather involved, requiring expensive equipment and training. As such, community awareness and the ability to fight mosquito breeding sites in resource-poor areas is low. Our approach to this problem is to apply TinyML to the acoustic monitoring of mosquitoes. In particular, TinyML provides an affordable solution for disease intervention, and once classification models are deployed, the device can conveniently and discreetly be placed in bednet corners or other areas of a home that typically serve as mosquito breeding sites. Ultimately, we hope that this sort of surveillance method helps reduce rates of deadly disease in high-risk regions.
We sourced our mosquito-positive audio from the Humbugs Universe dataset compiled in Tian et al. In 2020. And this generally provides 1-second audio recordings of various mosquito species from 4 audio locations. The audio recording labels have been crowdsourced to verify whether mosquito wing beat audio exists in the clip or not. To augment our data, we also adversarially trained against the speech commands dataset compiled by Warden in 2018, using the examples of noisy background, silent, and spoken command audio. Further, we took the CNN model outlined in Tian et al. As a baseline to compare against our model implementations.
Our implementation code was created by modifying the wake word detection example provided by TensorFlow Lite. As shown in this chart, the wake word detection workflow consists of 5 steps. We reused the same feature providing and command responding infrastructure from the wake word detection example and experimented with different model architectures for a particular use case. As shown in the 2 below figures, each 1 second of raw audio input data was transformed into its spectrogram representation using a variant of MFCC preprocessing, a method that, at a high level, uses a fast Fourier transform on the audio frequency to generate a numeric array. Here we show an example on the right of the waveform of a mosquito-positive audio file from Zooniverse, and on the left, its generated spectrogram input to the neural networks. To train the model, we used a dataset that contained all of the mosquito-positive Zooniverse files, as well as an equal percentage of audio clips containing audio that was silent, as well as audio that was unknown, which contained adversarial examples from the speech commands dataset. We ran all of our models using an 80-10-10 train test validation split. The neural network weights were also manually quantized post-training from float 32 to int 8.
First, we examined the impact of using logML versus MFCC preprocessing in the Keras implementation provided by Kiskin and others. After training, we found that MFCC preprocessing yielded higher accuracy and AUC results than logML processing did. We also refactored Kiskin baseline models to be compatible with the speech commands training and quantization scheme. Here, we only examined MFCC and micro preprocessing because logML was not implemented in the speech commands framework and could not be deployed on device. We also experimented with various CNN model variants. In the past, CNNs have been shown to work well for audio classification from spectrogram representations. So in our first set of experiments, we trained and tried to deploy a variety of CNN variants. On the left here, we have the architecture from our baseline CNN, which was based off of the TinyConv model from speech commands. Each window of the spectrogram is first processed through a 2D convolutional layer with 8 filters of size 8x10 in stride 2. The output of that layer is then passed through a ReLU gate and an FC output layer. On the right, we've listed the other variants we experimented with. In particular, for the CNN FC, we added 1 additional FC layer with 50 inputs and 50 outputs before the final FC layer. For the CNN2, we ran the tiny embedded conv model from speech commands, which uses a series of 2 convolutional layers with filters size 8x10, but with strides 2 and 8. For the CNN 4x5, we halved each dimension of the baseline CNN's filter, and for the CNN 24, we tripled the baseline CNN's filter count to 24.
We further also implemented the DSCNN architecture as inspired by the best model setup in Zhang et al. 2018. Here, it specifically features a depthwise convolutional layer, which separates outputs into different channels and provides, therefore, more channel outputs with an equal amount of computation compared to a traditional convolutional layer. For our two models used here, we examined whether or not adding the match normalization layer added or hindered model fitting due to the partial regularization that it entails.
In our experiments, we recorded each model's train and test set accuracies, F1s, and AUCs. As shown in this table, we found that the DS-CNN without batch normalization had marginally better performance than the other CNN variants. We were particularly interested in exploring the relationship between the size of each quantized model and its test set accuracy. All model architectures examined perform better than the Kiskin baseline models. Our chart also confirms that shallow networks can fit upon the dataset well and may be better suited to detecting highly regular audio data, such as Mosquito data. Additionally, we observed that dense layers in the baseline model may be exceedingly hard to fit well, and thus prevented model fitting.
For our next steps and conclusions, we note that it would be good to verify our models on live mosquito data, whether laboratory-based or in a wild setting. Further, we'd like to also evaluate our new model architectures on the same data set exactly as used in Kiskin and other literature to provide a more accurate comparison. With regards to other implementations, we hope that in the future, people could implement different pre-processing techniques such as wavelets or log-mel transforms on the device to see how they change model accuracy. And further, we'd like to see whether or not we could build a classification model for mosquito species level detection rather than simply audio detection solely. However, this would require a different dataset as Kiskin's does not include species IDs. Thank you so much for your time.